Okay, first of all, thanks for the invitation from the organizers and also for the opportunity to present the main result of my PhD thesis, especially in this crowd, because I think almost everything I learned on infinite dimensional geometry, I learned in some way from this crowd, or from their papers or from conversations, so I'm quite happy to present it. One short remark on the title. So I think Mañé's critical value itself is a tool from finite dimensional Hamiltonian systems, and the magnetic Hunter-Saxton system we will see is a nonlinear PDE. On the other hand, then we have here this interdimensional magnetic Hopf-Rinow theorem, and I will explain everything, but also explain how these different worlds belong together. And first, a rough plan for the talk. So first, I want to give you background on geometric hydrodynamics, recall what we have seen today, maybe also then we study toy models, magnetic geodesics on S3. Then we will generalize this toy model to infinite dimensional sphere. Then we will generalize the system even more to infinite dimensional D group, and we'll realize this system corresponds then to a PDE. And then we will see what it means for this system, how their Mañé's critical value come into the game, and how we get something like a Hopf-Rinow theorem. And then, if time permits, we will talk about related work and further directions. First of all, in Arnold's most cited paper, we had the following setup. So, in 1996, we have energy is a closed Riemannian manifold, and then solutions to the Euler equation of hydrodynamics, as Steve already mentioned, are in one-to-one solutions of the geodesic equation of the group of volume-preserving diffeomorphisms equipped with the L2 metric. And how is this going? Here first, the first remark that we can do the tangent space, so for its recall, tangent space at a group of volume-preserving diffeomorphism at a diffeomorphism phi is given as all vector fields that project down, such that the Lie derivative of this vector field of the volume form vanishes. And then we can define a Riemannian metric on this tangent bundle by integrating two vector fields over the whole manifold by using this Riemannian metric. And we see this Riemannian metric is invariant under the group action of the group of volume preserving diffeomorphism, and typically one uses here the right action. So far so good. And how is this one-to-one correspondence working? I think it's always either you start with a solution of Euler's equation, then we can define a flow by this equation, and we get then a volume-preserving diffeomorphism solving this equation, or the other way around. If we start with a diffeomorphism solving this equation, then we can go back by defining a vector field by differentiating our diffeomorphism with respect to the time derivative and pulling back that to the identity. And of course, that's way more things to do here, but so from a geometrical point of view, first remark is what I like to think about this the following setting. Either I have a really complicated equation on a nice space, or I have a nice equation on a not so nice space. But since I'm from geometry, I like to use the second perspective, since I'm familiar with that. So from a geometric point of view, what's the next step? Either we can change the group, or we can change the metric. That's the next natural step. And that was also done, for sure. So then we do a big time step, and by Boris Kizin and Jeremy Mijolek in their 2003 paper, I guess, they have proved that solutions to this non-linear PDE are in one-to-one correspondence to solutions of the following geodesic equation on the space of diffeomorphism, which are fixed in one point on S1, equipped with the H1 metric, where this group is given as all diffeomorphism on S1, which are fixed in one point. And this can be also identified with the space of probability densities. And H1 metric, for your convenience, I write it down on the identity, is giving H1 dot metric is given by integrating over the space derivatives of these two vector fields. And note here, the metric is again invariant under the group action of the group. So, and this equation will be improved later on. And it's the same procedure as before. And now, what's the next step through the lens of Hamiltonian dynamics? What about Newton equations? So we studied now particles without external force. Now we take the most easy force, like a potential force, and so for your convenience, Newton's equation, as this, you can write it down in this way. So we add a potential force, and of course we can ask, are there PDEs which can be written as Newton equations? And the answer is yes. There's a whole zoo on Newton equations which are PDEs, and this can be found, for example, in the survey paper from Boris, Jared, and Glass from 2021. And here, either if we go to the Wasserstein-Otto geometry, which corresponds to the L2 geometry, L2 metric on the first slide, or we can go to Fischer-Rao metric, which is more like H1, and there we get all these PDEs which can be written as a geometric equation. And through the lens of Hamiltonian dynamics, I think the next natural step is to ask, okay, what about charged particles? So can we describe a PDE as the equation of motion of a charged particle on an infinite-dimensional space? So what about, or in other words, using Arnold's definition of that is, what about magnetic geodesics? And for that, I define first what a magnetic geodesic is. So we take a Riemannian manifold equipped with a closed 2 form, and then we define a bundle endomorphism on the tangent bundle Y through this equation, and since G is non-degenerate as a Riemannian metric, this uniquely defines this bundle endomorphism. And then we call gamma a magnetic geodesic of strength S if and only if gamma is the solution of the following ODE. Here we see the geodesic part, and then we scale it here. And here this is the perturbation through the magnetic field. First remark to this. I like to think about this equation as a linear deformation of the geodesic equation, as Y is a bundle endomorphism on the tangent bundle, so it scales linearly in the velocity. So we deform, in terms of the velocity, the geodesic equation linearly. And if we put here S equal to 0, you get again a geodesic.
Gamma dot.
Where? Here?
Fourth line, right hand side.
Here? Here?
This is I and not marble. Okay.
Here? Okay. So, yeah.
Basic question. So if your manifold is scalar, for example, just a Riemann surface, it's like this map gamma, just almost complex structure. So somehow like does 90 degrees rotation. So you are so like magnetic geodesic equation means like you get an acceleration in 90 degrees rotation of.
Yeah, exactly. So if you choose M surface, then you pick like a Kähler metric and the corresponding Kähler form, then this Y is exactly a complex structure. But there are also more complicated scenarios, which we will see in our toy model. So we will now, since the geometry talk, we also go now to a toy model to illustrate all of this. And before I have to tell you the goal. So the goal is now to compare geodesic and magnetic geodesics by means of a Hopf-Rinow theorem. So how much we can deform the geodesic equation such that still the Hopf-Rinow theorem holds. So this is the goal. And for that, we go to a toy model. First, we write S3. This is the unit sphere in C2, where we equip C2 with its standard Hermitian product. Then we get the round metric by restricting the real part of the Hermitian product to the tangent bundle. And the standard contact form can be rewritten, has this expression. So we restrict this from the outer Hilbert space to our manifold itself, and we see the alpha is given that has this expression, so it's exactly the imaginary part of the Hermitian product restricted to our manifold. And then from contact geometry, we can define the kernel of our standard contact form as the standard contact distribution. And we can define the orthogonal projection from the tangent space at a point Z from from S3 to our standard contact distribution by orthogonal restriction. And then if we do some calculation, we see the magnetic geodesic equation for this system. So for S3 equipped with the round metric and the most canonical choice in some sense for a magnetic field, or the alpha, reads as follows. We have here the geodesic part, and then it's S times. And here we project down the velocity of our magnetic geodesic to the contact distribution, and then we can rotate in the contact distribution by 90 degrees. It's a bit more complicated, but related to what you said before. And then we can solve this equation and see, okay, this is joint work with my advisor Peter Albers and Gabriele Benedetti. So if we have this equation, we can solve it explicitly and see a magnetic geodesic has always this form. So we have here where P1 and P2 are complex orthogonal. So in some sense, it's always spiraling around on some torus. And we have some integrals of motion. The first is always the kinetic energy of a magnetic geodesic, is the integral of motion. And then we have a second integral of motion. And this is a nice geometric interpretation. We have here the velocity. And here, this is, from familiar with it, this is the rib direction. And we see the angle between velocity and rib vector field is the integral of motion. So if we start horizontal, for example, in the contact distribution, we stay horizontal. And since it's a geometry talk, we have now a picture how we can imagine that. And big thanks to Anna, who's also in the audience. She nicely agreed to make that picture for me because I'm not able to do it. So first here, we have S3, and we can chop up S3 into two solid tori. And then we see here in blue a magnetic geodesic, and as I said before, I like to think about spiraling around on tori. And here, this is, for example, this is a rib orbit, and so we see this is spiraling around. And here, this angle theta, this is the integral of motion. Since here, if you imagine, here's the velocity, and then this is the rib direction, and this is preserved at all points. And then the next thing is, one would think if we have here this magnetic geodesic and use the Hopf projection and projecting down to S2, then if we have upstairs fixed velocity and fixed magnetic strength, that downstairs we get like a magnetic geodesic also of fixed strength and fixed velocity. Or in other words, the radius of this blue circle downstairs is fixed. But unfortunately, that isn't the case. Since if we project if we start here in Hopf direction, like here or in this direction of this orbit, we stay on this orbit and we only follow this orbit, and this orbit projected down with the Hopf projection is a point. So we can get downstairs points, but also we can get downstairs great circles that are connecting these and these points. So in other words, what we figured out is we can recover all magnetic systems downstairs at once from the magnetic system upstairs at once. So this system is way more complicated than this. And now we come to we go back to the focus. We want to think about, okay, what's a Hopf-Rinow theorem? And we will see on the next slide. We can connect all 2 points below some threshold of the magnetic strength on S3 with magnetic geodesic. And then I'm spoiling already, but above some threshold, it's not possible to connect this orbit and this orbit with a magnetic geodesic. It's not possible. And this is exactly on the next slide. So what I said before, all points on S3 can be connected by unit speed magnetic geodesic of strength S, if and only if S is between 0 and 2. That's the first thing. Second thing, for all S bigger equal to 2, there exists no unit speed magnetic geodesic of strength S connecting these 2 orbits. It's not possible. It's a special case of our theorem, but let me state it in this way. And now the explanation. First remark, this threshold at 2 is exactly Mañé's critical value. So we see exactly at this threshold, the dynamics change drastically. Then a second remark, in finite dimensions, this implication one would also follow from a way more general theorem from Contreras, but we proved it independently with the hope to generalize it later to infinite dimensions, where this theorem does not hold, since it's limited to closed Riemannian manifolds. And the last remark, for strong magnetic fields, we have no Hopf-Rinow theorem in terms of geodesic convexity. So, and now before we move on, we will talk about what is Mañé's critical value and how we can define it, and maybe only shortly discuss why this value detects this change in behavior. For this, a short remark, we see gamma is the solution of the magnetic geodesic equation. So this equation, if and only if, gamma is the solution of the corresponding Euler-Lagrange equations of the following Lagrangian. This is standard procedure, and you may know it from physics, but maybe if you go back to your physics course, solutions of Euler-Lagrange equations are also one-to-one to solutions of critical points of action functional, and that's the next thing. What we see, okay, gamma is a critical point of the corresponding action functional, so this is a if and only if, so we can switch between them through it. And now we use the formulation with the action functional to define Mañé's critical value, and here that's the next slide. So first note, so fixing the energy value is up to reparameterization the same as fixing the magnetic strength. And for defining Mañé's critical value, it's more convenient to fixing the energy value. But for the rest of the talk, it's always more convenient to fix the energy and switching the magnetic field. I'm sorry for that, but otherwise it doesn't make sense. So we fix now magnetic strength, and then we see, okay, we have M, possible Hilbert manifold, equipped with the Riemannian metric, and an exact 2 form. This is our magnetic system. Then we can define the Lagrangian in this way. So here, this is the kinetic part minus the part through the magnetic field. And then we define CL, the infimum over all energies, so that the action functional is positive among evaluated on all periodic orbits. And now I explain why this thing is kind of natural to say. So writing this down, this is this is the action functional of energy k. So this is our Lagrangian, and then we can add here this energy term. And in case of geodesics, if we don't have here external force, right, this is always positive for all k. So we try to mimic the case of the geodesics. So for geodesics, this is 0, then this would be always 0, and then we try how less we can make the energy so that it still mimics the geodesic action functional. And from the slide before, we have seen, okay, if we have a magnetic system, we get a unique Lagrangian. So we define now the Mañé's critical value for our magnetic systems through this value. And first observation, it's intrinsically really hard to compute. But we managed to do it, and also this definition also holds for Hilbert manifolds. I think we can generalize it later on also in the other more setting. And now we go back to our system before on S3 and ask, okay, how we can generalize this system. First, the first possible generalization would be like on complex ellipsoids. I think that's really the one of the first natural steps. This is done with Lina, will be next week also here, and Tom, my co-workers, and it's work in progress. Then the second thing would be like magnetic billiards on S3. This is done with Johanna Bimmermann, who will be also here next week, and we used it to tackle problems in synclectic geometry. This is quite cool. And then the last thing, possible generalization, okay, go to infinite dimensional spheres. And since we're here on a conference, infinite dimensional geometry, we will do this. So going back to the setting on S3, if we look closer here to this, we see we only use the structure of the ambient Hilbert space on all of this slide. So what we can do, we can replace C2 with our favorite Hilbert space.
with the space of complex valued functions from S1. Then we get a unit sphere, the L2 sphere. We have again a Hermitian product on the ambient Hilbert space. So we can define by restricting the real part, the round metric on the sphere. We can define also what it means to be like a contact form, this alpha, we can define in the same way as before, checking that the co-kernel has codimension 1 and get exactly the same picture as before. And we see the magnetic geodesic equation reads exactly the same as before. And so it should be no surprise that we get a dynamical reduction theorem. So if we have a magnetic geodesic on S infinity with given initial data, then this gamma stays always on a totally geodesic embedded free sphere in S infinity, and it is flow invariant under the magnetic flow. How I like to think then about this is that means we can reduce the whole dynamics from S infinity always to S free. And this is part of the next slide. So also the Hopf-Rinow theorem. So for all points in S infinity, there exists a unit speed magnetic geodesic of strength S connecting these 2 points if the magnetic strength is between 0 and 2. Then second part, for all S bigger or equal to 2, there exists no unit speed magnetic geodesic of strength S connecting the constant function 1 and the identity. And if you go into Fourier modes, this corresponds exactly to this orbit from the S free and this orbit. It's exactly the same. And then, next remark, t equal to 2 is exactly Mañé's critical value. So if you do the same computation for Mañé's critical value as on S free, you can do here the same, and you get again, okay, this threshold where this Hopf-Rinow theorem changes is Mañé's critical value. And next remark, unfortunately, we can't apply this heavy theorem from Contreras anymore, or fortunately, depends how you view it. And now we want to go more to the PDE side. And so we have to generalize our magnetic system even more. And this is part of the next slide. So Jonathan Reynolds proved in 2013 that this map from an infinite dimensional Lie group equivalent to H dot metric from the second slide, which is exactly a Madlung transform, is an isometry between this infinite dimensional Lie group and an open subset of an infinite dimensional sphere equivalent to L2 metric. And here our group is a semi-direct product of the group of diffeomorphisms fixing 1 point on S1 and C infinity. And this open subset U, this is the space of all non-vanishing functions on our infinite dimensional sphere. And this is an isometry. But we have seen on the slide before, we have here more structure. We have here magnetic system. So we can restrict it also to this open subset and get their magnetic system. So we can pull back this magnetic system to this space so that we get a dynamics preserving map between this side, and this is done by myself. And I thought it's better to highlight it in blue, but that was a dumb idea. But we see we get a dynamics preserving map, so which I call magnetomorphism between this infinite dimensional system and this. This side we can understand quite well. This also, and the Madlung transform can be extended here to magnetomorphism. And first remark, I'm quite optimistic that this can be also extended to this LP Fischer-Rao metrics defined by Martin Bauer, Le Brigand, Liu, and Maier, if it's of interest, because there also you use kind of something like the Madlung transform. But that's only a side mark, so we can now study magnetic geodesics here on this space. And before we move on, I explain why I think this is the natural next step of a space to think of, since we see this space is over the cotangent bundle of the probability densities, pre-quantization bundle in the space of in the Fréchet category, since we have here or S infinity is a Booth-P1 bundle or pre-quantization bundle over CP infinity. So also U is then kind of a pre-quantization bundle over the projectivization. The projectivization of U is due to the work of Boris, Klaas, and Jared Majolek in Kähler isomorphic to the cotangent bundle of probability densities equipped with the Sasaki-Fischer-Rao metric and the canonical symplectic form. And our space exactly sits here as a S1 bundle over this space. And this diagram is commutative. So that's why I think this is a natural first, why this form here is canonical. And now we're in the position to study PDEs. First result, so if we go on our Lie group G and take some Sobolev order, which you can ignore for a moment if you like to, then we see phi tau, so a curve in this semi-direct product is a magnetic geodesic for this system which we introduced before of strength S if and only if the corresponding U and rho are solutions of the following nonlinear PDE, which I call the magnetic two-component Hunter-Saxton system. So we have now a magnetic geodesic, which is a PDE, and vice versa. Remark for this, the magnetic two-component Hunter-Saxton system is a linear deformation of the two-component Hunter-Saxton system underlined in red. And why is it a linear deformation? Since for S equal to 0, we get exactly here the Hunter-Saxton system. And this is a geodesic on an infinite-dimensional Lie group. And as I told you before, I like to think about the magnetic geodesic as a linear deformation of the geodesic equation. And so we see how we can deform it. And then, last but not least, this equation has also blow-ups as the original two-component Hunter-Saxton system. But we would like to use, now on the next slide, we want to use geometry to detect blow-ups and explain why we have blow-ups and also how to overcome blow-ups. I think that's related to Tobias' questions before, in Steve's talk. So we see, so we start with a solution of our PDE. That gives me here magnetic geodesic in G. And then we can use the Madelung transform to map this magnetic geodesic in our Lie group to a magnetic geodesic here in green on our infinite-dimensional sphere. And then we see if this magnetic geodesic on the sphere hits the boundary of our open set U, this is if and only if the case if the PDE, the magnetic two-component Hunter-Saxton, has a blow-up. Here what is written what I mean by blow-up, but this is this if the first derivative explodes. But if you see now, a magnetic geodesic on an infinite-dimensional sphere has no blow-ups, right? So what we can do, we can continue here the magnetic geodesic beyond this boundary. We extend it beyond this by following only the magnetic geodesic. And then we map back with the inverse of the Madelung transform this to the group, so we can extend then in some weaker setting the PDE beyond the blow-up. So that's like the geometry of global weak solutions. Of course, there's a lot of analysis that we have to do, but that at least to me, it tells me what to do. And then this is exactly the next slide. So we have, this is the natural completion of our group G, where we have, where this is the space of almost all absolute continuous function, non-decreasing, and having this property. So it's kind of, in some sense, the completion of our group G before, or you can also think of it as the space. Here you can replace absolute continuous with a Sobolev order of 1. And then we see, okay, by the geometric idea before, the weak magnetic flow on this space exists globally. And by using this duality between magnetic geodesics and solutions of the PDE, we get also global weak solutions. And first remark to this, for S equal to 0, this was proven by Markus Wunsch. And we extended it to the magnetic geodesic case. And then we can use this and this description before to get now for this on this space kind of a Hopf-Rinow property. So Mañé's critical value for the two-component Hunter-Saxton system. So if S is less than 0, there exists for all points GH in this space a weak unit speed magnetic geodesic of strength S connecting the identity, which you can think of as the North Pole, and any point. Then, but if S is bigger or equal to 2, there exists no weak unit speed magnetic geodesic phi tau of strength S connecting the identity 0 and this. And in Fourier modes, that's exactly this orbit and this orbit from before on the S3 case. And this is, and here again, this C2 is Mañé's critical value. And what is the state of the art? So what's the state of the art is we have here the tangent space at the identity. I like to think of here in this space, I think there lives the PDE. And then by this correspondence, we can use this duality, we can transform, use the solution of the PDE, map it to a magnetic geodesic here in this space. And by the Malung transform, we know we can map it to a magnetic geodesic in U. Magnetic geodesic in U is also magnetic geodesic on S-finity. And we have at the beginning this dynamical reduction theorem that tells us we can reduce all, we can also reduce here our problems always to a totally geodesic embedded free sphere. There we have an explicit solution formula, can try to tackle it there with calculations. And then we go all arrows back, and then we try to use with this magnetic flow on S3 to tackle these PDE problems. Questions so far?
Yes. I think I only know the very classical definition of magnetic transform, which sends two quantities like the magnitude and the phase to a complex valued function. It sounds like you are using this magnetic transform in a very generalized sense. Could you quickly recap what this is doing?
Can you recall the question?
Yes. Magnetic transform, I know, is very simple.
Yep.
It's just a map from magnitude and phase to a complex valued function. And I think your magnetic transform is much more generalized. I think from some cotangent space to space are some complex valued functions, but sorry, I didn't really catch it.
I think that I guess we're speaking about the same Madelung transform, but I think this that was also carried out, for example, by Boris Kesin, Jeremy Jolik, and Lars Mulin in their paper, The Geometry of the Madelung Transform, where they proved that this it preserves a lot of structure. The spirit is.
But yes, I know the definition given in that paper as well. But I think your version is kind of more generalized because you have something written U in the right hand side and you have some group in the left hand side.
Let's discuss that later. Okay. So this is state of the art, and I think then okay. So what now we can
go to related results, related work. So the first question is, okay, are there more PDEs which can be rewritten as magnetic geodesics? And the answer to that is also yes. So by the first thing, one can realize the KdV equation is also magnetic geodesic equation of the space of diffeomorphism equivalent to F2 metric, and magnetic field is this Gelfand-Fuchs cycle, co-cycle. And then this is written in this way, where we see here, this corresponds to the geodesic part, and this corresponds here to the magnetic part. So we see again, we can think of KdV as a deformation of the geodesic part. Next thing would be, okay, yeah.
Is it exact?
You can also take, you only need that it's closed.
Like for the beginning. You only need the exactness if you define or some sort of exactness for Mañé's critical value, but not for the magnetic system. So in the same lines, also if you under Kamas-Holm is also magnetic geodesic equation, only if we change here the metric to the H1 metric. And here again we see this is the geodesic part, this is then the magnetic part, and this follows from a more general observation. So what this is work in progress. This follows from the following observation that if we have a regular Lie group and here this closed two form, which is bi-invariant under the Lie group action, then we see gamma S is a geodesic and the central extension of this Lie group equipped with this metric G. If and only if gamma is a magnetic geodesic of strength S in the magnetic system on the Lie group where we removed the central extension. This follows more or less if you write down exactly the equations and then double check. And then from this observation, it follows more or less directly what I stated on this slide before, because if the Virasoro group is the central extension of the diffeomorphisms group with respect to the Gelfand-Fuchs co-cycle, and KdV is a geodesic equation on the Virasoro group equipped with the L2 metric, which is proven in 87 by Boris Kisin and his collaborator, and on the and Kamaso-Holm is a geodesic equation on the Virasoro group equipped with the H1 metric, which was proven by Majorlek, and all of this is part special case of this paper from Boris Kisin and Jared Majorlek from 2002, where they prove it for more general H1 metric. And then we can go to further direction to close off. Yeah.
It will be exact, I suppose. On the Virasoro group, it will be exact, I suppose.
I'm not sure, to be fair. But let's discuss that later. Yes.
So we get more of them. What it is, before I used this geometry to tackle also analytical problems. Here, to be fair, I'm not sure if we can use it, but it would be cool. And then, last but not least, more to Hopf-Rinow things. I think Hopf-Rinow theorem is false in general for Hilbert manifolds, but there's this result from Martin Bauer, Philip Harms, and Peter Michor that if you have a nice Lie group equipped with a strong Riemannian metric and some technical conditions C, then this Lie group is geodesically convex, so we can connect all 2 points with a geodesic, and this is I call strong Hopf-Rinow property. And it would be really nice, so this is a question then, okay, does for energies above a Mañé's critical value for magnetic systems on such Lie groups where we equip it with a magnetic form, does they satisfy some strong Hopf-Rinow theorem? That would be really intriguing, but to be fair, I have no idea how to prove it. And last but not least, I think that we skip. Thank you for your attention.